I'm Matthew.
I'm Bailey.
And here is our Senior Design Day presentation. So to begin, here's our problem statement. So we were sponsored by a company called Shadotech, and they are located in Carrollton, and they make window fashions, custom. So our problem was to solve the manual process of the Unishades product. So the process includes cutting the fabric to a specified length, placing a header and heat pressing. So that's the measuring. Then here we have the heat press. And then the third.
Eagle alert. Test this as a test.
Then the third process is to place plastic carriers through the fabric. So for our objective and scope, we are focusing on the first two processes, which is measuring and cutting the fabric and heat pressing the header, the nylon header onto that fabric. So here we have the fabric measurement, the fabric cutting, the header placement, the heat press, and we are aiming to improve the repetition of cycles, and we left out the plastic carrier placement due to time constraints. So here you can see our objectives and requirements. So here we have our business requirements such as fabric cutting and pulling fabric, along with their engineering requirements such as an eighth inch of a tolerance. And the very last one, efficiency, which was most important to us, the minimum of 40% improvement on this process.
So our design process and our milestones, we base our milestones off of the structure of the class, which is broken down into a series of reports and presentations that we have to complete. First, we have our systems requirement review, and we have the dates, the target and actual date for each of these that you can see. And the goal for the SRR is to evaluate completeness of the requirements. So basically get a full understanding of what we want out of this project. We then moved on to the PDR, Preliminary Design Review, where we made sure that our early concepts, the key design decisions were well reasoned, and that the design has been carefully considered and evaluated, basically making sure our early ideas, we can push through with them, there's merit to them. Then we have our Critical Design Review, and this is where we make basically not the first draft, but we demonstrate the readiness to transition into the next phase of the project, prototyping, assembly, and testing. So we have the modeling of everything complete, and we can say from this point, we can go through and make this machine. Then the Test Readiness Review, TRR, is where we ensure we are ready to test each of these and go back to our requirements and make sure that each of the requirements is accounted for. And then finally, we end with the Systems Acceptance Review. And this just confirms the system meets all the requirements, performs as intended, and it is ready for delivery to our sponsor.
So here's a visual representation of those milestones. So here's our Gantt chart, which shows the, the system requirements review, the preliminary design review, the critical design review, test readiness review, and the system acceptance review. So that's the distribution of the dates on which those milestones occurred.
Now going into design evolution, we first started with concept generation, where we all just took pen to pad, whatever idea we had, we put it on the paper, and then we met with our sponsor, said, what do you think about these ideas that we have? From this point, we move on with all these alternative choices we've come up with and use a decision matrix, in this case a Q matrix, to decide which one of these makes the most sense, would be the most optimal for us to go through with. And here for the motion system, we chose V-rollers and timing belts. For cutting, we are using a rotary blade. And then for the header press, we have a header spool provided by our sponsor, which will also be cut using a rotary blade. And then here's our initial CAD model. This was the first draft that we made of this before any optimization. And here's where we use all of our inspirations, such as the motion system of 3D printers or the heat press of a t-shirt press, to come up with all of these concepts. Moving on, we have design evolution continued. The final CAD model, this is what you would have seen in our booth out in the hall. We have first the main pulling system. Along that rail is where the fabric is pulled to our final length. Here too, we have the header cooling system, which we would have the header spool right there, and it is pulled to length, cut, and then placed where the fabric is. And then we have rotary cutters here for both the fabric and the header, and the heat press here. Here are pictures of our final machine. And now for engineering calculations.
Here's the quick calculation that we did to make sure all machine is safe to build. So the first the calculation that we did is the deflection for header and basin, and flat T strength of the header press and motor torque of movement for the fabric, and the load capacity of the cover board and big package here for the cover board that I showed the picture right here, and the loads for aluminum sling and length and cutting fabric force torque required to fasten the bolt. And here's the main simulation, the main table simulation that we using the SolidWorks to do simulation. So the first one, the first picture is the stated displacement. You can see there is the red spot. There is the weak part. So we have at the 2 bar under the main table to support it. So and the strain and stretch stated that we show right here is show green to blue, so which is really safe to handle that stress and strain. And the third one is the fourth one is the factor of safety for the main table. It's 2, so that means it can handle like twice at the stress that I had applied. So here's the header spool table simulation using SolidWorks. So displacement and strain stretch stated is show like from blue to green. That means it's really safe to handle the stretch and strain. And the facultative safety we have for the header spool is 5.8. So that means it can handle like five time of the stretch that I have applied.
Over here we have the manufacturing, assembly, and testing slide. So the machines we use, we didn't need to use all of these machines, but we had access to a lot of them. So we use a manual and CNC mill, a CNC router, a water jet, and 3D printer for some of our parts. Due to limited access, we could have used a laser to cut a lot of these parts, but our laser is not powerful for some of the materials, so we opted for the other machines we had access to. Because some of the parts needed to be more precise, we did use our CNC mill and our water jet, and other than that, it was mostly manual machining, or the parts were already to length, ready to be used from the source. For our testing plans, we wanted to make sure that our microcontroller and our touchscreen display work together. Our individual components needed to meet their requirements, and our full system, all components need to work in sequential order. So for assembly, we ran into a few things. For our screws, we had to put some washers in just because they were a little too long for our corner brackets. Over here you can see some of the assembly happening. We had a little fun getting trapped inside of everything. It was a really fun time. We have as well the results and findings. Our touchscreen, we have a lot of different settings here. If you saw me out in the booth, you saw me explaining it. We have our settings, which is password blocked, and it goes into our temperature screen where you can change it. Sometimes you need more temperature, sometimes you need less, depends on what you're doing. We also have our control screen where you can manually operate all of the motors, pistons, whatever you need from that screen. We also have this screen, which is the main running sequence where you can set your length of your curtain, how many curtains you want, and it'll only activate after you've set that within the correct parameters of the length of the machine. You can see at the bottom, there's a red box. That means it's not set at all. Now it's green. That means you can run it. We needed to make sure that we followed all of these, and we have accurately hit every single, individually we have hit every testing situation that we need. for testing, we have individually blades cut in one pass. We have all of these different tests we've completed individually. Our next results, or our next steps are to get a full cycle of everything working together, but individually everything works.
All right, on to risk assessment. So like with any project, there's many risks involved, so we made a list of them. I'm gonna highlight a couple of them today. So the first one is operator injuries, which is a major concern and was highly considered during the design of our product. So as you can see here, it started in the severe and unlikely category, but after mitigation and adding safety features, it moves to major and rare, which is as good as it can get at this point. And then next is header press overheating. That's a major concern with safety as well, and also heat, fire can be an issue. So that was in severe and unlikely as well. And then that moved to significant and moderate with adding the temperature sensors and other parameters in place to mitigate that. And the last one I'll talk about is inaccurate measuring. So our product needs to be very precise. So calibrating everything is very important for the success of the measuring. So that started in a major and unlikely, and now it is in minor and rare. And then on to safety. Safety was something that we considered during every step of the product or the project. It included safety features that we included in our machine, which was e-stops, warning stickers, plexi barriers, and surge protectors. And then also while we were manufacturing these, we made sure to take those safety precautions as well. So we all got machine trained for safety and the mill and lathe. Safety glasses and gloves. As you can see, here's Becca with a grinder, wearing her gloves and her PPE. So
Stuck it on my fingers.
Yeah, we're all good. Yes, and then so onto our budget overview. So originally we're slotted $2,000 for our budget, but when talking to our sponsor, we were given a little bit of leeway there. And so after we calculated everything, it was around $2,300. But as you know, you run into unexpected things, so now it's closer to $2,700. But I'd like to say at this point, our sponsor showed us a machine that he could have purchased for $9,000. So as we think this is pretty good considering. And so we did in fact fully automate the machine. And we also had some donated materials from the UNT machine shop. We had a previous design project that we borrowed parts from. And then some other things that we did. And this is a little bit of our budget overview. A lot of our stuff that we got was from 80/20, which is a manufacturing supplier. Those were our aluminum extrusions, which is the main system. And then, miscellaneous other things equating around $2,700. And so with any project, ours isn't perfect either. So we have a couple things that we can do in the future. So if this was to get passed on to another group, the main thing would be adding that carrier placement, because we had to eliminate that from our scope. And then there's just some things that we could add to make it better as well. So we incorporated those. So do y'all have any questions for us?